So let's take a look at section 3.4. So in that section, we're going to look at two things. First thing is what's called the rational root theorem. The second thing is synthetic division, which is a nice way to use, it's a nice thing to use in place of long division when you can, because it's very fast. It doesn't take up a lot of space on the page either. All right, so when we're finding roots, okay, when we're finding zeros, when we're finding where a graph crosses the x-axis, all the same thing. Sometimes you might have roots that are rational, sometimes they're irrational. What does it mean if something is rational? What's the difference between a rational number and an irrational number? Rob? Well, rational and irrational both fall under reals. In fact, that's the definition of reals. If you take all the rationals and irrationals together, those are your real numbers. So they're both real. But does anyone remember the difference? So rational numbers are numbers that can be written as a fraction. Okay. Irrational numbers are numbers that can't. So we're going to look at a theorem that will help you find all rational roots. Hence, it's called the rational root theorem. So, to use this theorem, they'll give you a polynomial. Okay, when we do an actual problem, just to kind of skip ahead and show you, it might look something like that. 10x to the fifth minus 3x squared plus x minus 6. But in general, it'll look something like that. So you'll have a polynomial, and there's only two things there that will control the rational roots. There's going to be a bunch of numbers, but the only ones that are really important are two of them. And I'll show you which two are the ones that are important. Great. That's just fancy math language. I'll translate it if you want to write it down translated. But what it's basically saying is that every coefficient in front, the ones I'm circling right now, and the constant, they are all rational numbers. So all the coefficients are rational numbers, and the first coefficient and the constant cannot equal 0. Okay. So it's just kind of a fancy way to write it. So all the coefficients are rational numbers, and the first coefficient and the constant are not equal to 0. That's all that says. So what I'm saying is, if you had a problem like this, you can't use the rational root theorem on it, because you just told me the constant is 0. Doesn't work when the constant's 0. Okay, so can't use it in that case. You also can't use it if your numbers in front of the variables are irrational. So if you told me this, minus, yes, that is a quadratic equation, but the problem is the numbers in front of the variables are irrational. Square root of 3 cannot be written as a fraction. Pi can't be written as a fraction. So you couldn't use rational root theorem on a problem like that. So if you have a rational root, it can be written as a fraction. I'm going to call the fraction p over q. The only question is, how do you get p? How would you get the top of the fraction? And how would you get q? How do you get the bottom of the fraction? Well, it's going to come from two things in the polynomial. P has to be a factor of the constant. Right? So if you're trying to find rational roots, the numerator of the rational root, okay, the numerator of your fraction, always has to be a factor of the constant. The denominator is a factor of the leading coefficient. And so if you have a polynomial and it's going to have rational roots, it has to fit this definition. The The numerator of the root will always be a factor of the constant. That's this number. And the denominator of your rational root will always be a factor of this number. So to find rational roots, the two things I circled in red is all that matters. Nothing else plays a part in it at all. Now, we're going to be generating a list of possibilities. Not every single possible number that we write in this list is going to be a root. Right? The rational root theorem gives you a list of possibilities. It's still up to you to check which of those possibilities actually work. And to do that, that's where the calculator comes in. Without the rational root theorem, we wouldn't even know where to start. But the rational root theorem basically gives you a starting point. And then we go from there. Okay. So I'll mention that again as we do an actual problem. Okay, so I want to list all the rational roots in that problem. So the first thing you want to do is use the rational root theorem to generate a list of possibilities. Then we'll use the graphing calculator to eliminate the possibilities that don't make sense. So if there's a rational root, it's going to be of the form P over Q. P, if we go back up, are the factors of the constant. What's the constant there? Negative 6. What are all the numbers that divide into negative 6?
1, 6, 3, 2.
So 1, 2, 3, 6. I agree with all of those. And there's 4 more. What other numbers divide into 6? Yep.
-1, -2, -3, -6.
Yep. So we have plus or minus 1, 2, 3, and 6. Those are all the factors of the constant. Okay. What are all the the next thing is Q. That's the leading coefficient. Emily, what's my leading coefficient? 10. Yep. And what's all the numbers that go into 10?
1, 5, 2, 10.
All right. So 1, 2, 5, 10. Anything else?
Plus or minus.
Plus or minus. Yeah, it's always plus or minus. So now what we want to do is generate a list of every possible P divided by every possible Q. Kind of seems like it could be a lot, but as long as you do it systematically, it's really not that bad. So we'll call this a list of possible rational roots. Okay, and I'll do the first part. So let's start with P equals 1, okay, plus or minus. You could have 1 over 1. You could have 1 over 2. You could have 1 over 5. And you could have 1 over 10. That's every possible denominator with a numerator of 1. Now let's go to the next one, 2. What would be my first P over Q that I could have if the numerator was 2? Yeah?
2 over 1.
Yep, 2 over 1, which I'll just write as 2. What would be my next one? Okay.
Plus or minus 1.
Yeah, it would be 2 over 2, but I already have that one from earlier. So I don't need to, I did 2 over 1, 2 over 2 I already have, 2 over 5, and then 2 over 10. So we don't have 2 over 5. And we don't have 2 over 10.
But you have 1 5.
Yeah. Yeah. And we might even see these other numbers again later on. So yeah, it's always a good idea to reduce it. So that's every number you could have with the denominator, all the different denominators that have a numerator of 2. And then we reduce some of them. What would be my next row? Yep, Ron?
Plus or minus 3, plus or minus 3 over 5, and plus or minus 3 over 10.
So we have 3 over 1, yep. 3 over
2.
3 over 2, we don't have that one. 3 over 5, no, we have 2 over 5, we don't have 3 over 5. And then 3 over 10, we don't have that one. And then the last one, we'll do it with 6. So 6 over 1, we don't have that one. How about 6 over 2?
You have that, it's 3.
3, we already have that one. 6 over 5, I don't think we have that one. Plus or minus. And how about 6 over 10?
We have that one.
We already have that one. So now, what that list means is that if this graph is going to cross the x-axis at a number that can be written as a fraction, it has to be one of those. I'm not saying it's all of those. I'm just saying if it crosses the x-axis somewhere, that's a fraction. It has to be one of those numbers. It has to be. So now I could graph it and kind of notch it.
You have 1 over 5 written twice.
Did I write 1 over 5 twice?
Yeah.
Okay, that's okay. So we wrote it twice. We really don't need it twice. So we have a list of 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, double it for the positive, negative, a list of 24 possible places that it could cross the x-axis at a fraction. But if I look, it looks like positive 6 and negative 6, that's as big as these fractions go. Everything else is between positive and negative 6. So when I graph it, I'm just going to set my window to be, I'll just leave it at the standard window, negative 10 to 10. That's plenty to see all these values. So let's graph it and see what we got. So 10x to the 5th minus 3x squared plus x minus 6. Okay, so this first step, I call this just generating a list of possibilities. Now I'm going to look at the graph, and I'm going to narrow that list down by looking at them. Okay. I don't want to rewrite the whole list, so I'm not going to rewrite it. I'm just going to cross out ones that don't make sense. I think plus 1 looks like a good candidate right now. How about minus 1? Does that graph looks like it crosses anywhere near minus 1? No. So I don't think it's going to be the minus. How about plus or minus a half? Does it look like the graph crosses near plus or minus a half? No.
I'm confused. Why would you get rid of the plus or minus 1? It crosses...
I think it crosses near plus 1. I'm going to check it out later, but I crossed out the minus.
Oh.
Just the minus.
Okay.
Does it look like it crosses near plus or minus 1/5?
No.
No, that doesn't look like it's going to work. 1/10?
No.
No. 2?
No.
Not really. 2/5, which is like 0.4?
No.
No. 3? No. Plus or minus 1.5? Not really. It's not near 1.5. 3/5 is 0.6. No. 3/10, 0.3? No. Plus or minus 6? No way. It's not even close. Now, you could make an argument for 6/5. Because 6/5, if you divide it out, is 1.2. Well, I'd say, I wouldn't say that that's unreasonable to say. It looks like it could be close to 1.2. I still think it's 1. I definitely don't think it's near negative 1.2. So out of that list, the only ones that, if I look at that graph really fast, that even seem remotely reasonable are plus 1 and plus 6/5. All right. Now, I'm actually going to check it and see which one of those is correct. So I'm just going to do trace, and I'm going to guess 1, and hope that when I hit enter, I get y equals 0. Nope. So even though 1 looked like it was a root, it's not. So 1's not a root. Let's check 6/5. I don't think that one's going to be either. So 6/5 fifths.
Wait,
No.
how do you do that?
I just use trace. You could do the same thing by going to the table.
I can't, like, it's not letting me,
Type in a value.
yeah.
Are you using one of mine?
No.
No, it could be a setting I could take a look at.
Okay.
But let's just go second calc 0. Let's see what the root actually is. So I'll pick a point left, right, and do a guess. The actual root is 0.95. So what does that mean about that number, 0.9505? It wasn't in this list. So what kind of number must it be? Yeah,
Irrational?
it must be irrational. So this particular problem had no rational roots. And I can prove it because it's not in this list. It has to be in this list if it's rational. I actually think that's example 2. Let's see. Is that the same one we just did, 10x to the 5th?
Mm-hmm.
Yep. So now example 2 says, show that that example we just did has one real root, and that it's irrational. So the way you would write it is you'd say the root is at 0.9505, and this is not a number that was in our list of possible rational roots. And this is not a number in the list of possible rational roots. Well, if it's not in the list of rational roots, there's only one other number it can be, and that's what Evangeline said, it's irrational. So, 0.9505 must be irrational. Has to be. So that would be a problem when somebody had asked me about the homework. Is there another way we could do this problem without a calculator? This one, no. Because the root is irrational, there is no other way with the level of math that we know right now to do that problem without a calculator.
Is there a way without a calculator?
Yep, there are methods, yeah, to get that. Probably not, it's not really something we're going to look at. But yep, there's all kinds of methods in math to like approximate answers as accurately as you want. So it just takes more time, but you could get an approximate answer to as many decimal places as you want. Now, could you get an exact answer? But like, you know, the quadratic formula gives you an exact answer, but you can't use that here. I don't know if you can get an exact answer. I'm not sure. I'd have to think about that one. I don't know how to get an exact answer. I know how to get a decimal to as many decimal places as you want, but it would just take me a long time, depending on how much accuracy you want. So any questions on that? All right. So that's the rational root theorem. Okay? Just gives us a quick way to test for rational roots. Yeah, I think we'll come back to it a little bit more. Let me just jump ahead. Synthetic division. Yeah, so we're going to use the rational root theorem again in a little bit with synthetic division. Okay, so let's look at what synthetic division is. So as long as you want to divide by something linear of the form x minus c, it can't be x plus c. If it's x plus c, you got to rewrite it. It's got to be x minus and then a number. Well, let me let's see. Do I have the example? Yeah, I'll show you the steps like I did yesterday, and we'll do an example at the same time. All right, so to do synthetic division, you're going to start by writing down the number that's after the minus sign, okay, on the outside of a little bracket. And then all you're going to do is write down the coefficients. You're not going to write down any letters in the whole process of synthetic division. Okay, so let's look at our problem. I don't see any missing powers. Cubed, squared, linear, constant. So that part's good. And the directions say show that that is a 0. Show that 3/2 is a 0, which means show that 3/2 is a root. Show that 3/2 is an x-intercept. Those all mean the same thing. But there's one other way we can show it, and that's how we're going to use synthetic division. If 3/2 is a 0, then what is a factor? Yep.
X plus 3/2.
Not quite. Close. If 3/2 is a root, think about if you had a problem like this. Let's do. And I told you that negative. Let's see, with that factor. It's hard to make one up that works. Let's try. Make that an 8. Let's see if that would factor. So you get I'm going to factor it, then I'm going to erase it because I want you to kind of work backwards and see. So if I did minus 8 minus 1, so let me just change that to a 9. And now that should factor. 8x squared minus 8x, yep, side factors. So, kind of already know the answer, but if I told you that 1 is a root, if you plug in 1 for x, I guarantee you will get 0. So 1 is a root. So what does that mean would be a factor of that problem? Yeah?
Like 2.
Well, no, it's one of the things I just had written down before I erased it. If 1 is a root, what's one of the factors there? Yep.
X minus 1.
X minus 1. Now, the other root was 8. So if I tell you 8 is a root, then what else is a factor? Yep.
X minus 8.
X minus 8. So it's always x minus the root. So now in this problem, I'm telling you 3/2 is a root. So what would be a factor if 3/2 is a root?
Allie said it.
Oh, did you?
Yeah, that's what I said.
Yeah, that's what when you asked about the minus 1, she actually said.
Oh, okay.
The answer
I'm
to
sorry.
the one.
So x minus 3/2, that's your factor. So what we're going to do is take this.
Wait, I'm confused. I'm very confused.
Okay.
So what we're really doing is, if you're asking me to prove that something is a 0, okay, that's the same as proving it's a root, just a different word. Or it's the same as showing that if I divided this by x minus 3/2, I get a remainder of what? 0. That's what I'm really going to show. So I'm not going to directly show that 3/2 is a root. I'm going to show something else that means it's a root. I'm going to show you that if you divide by x minus 3/2, you would get a remainder of 0. And that means 3/2 is a root, or a 0. Okay. Any question on that idea? It's really the only way you can show something is a 0 using synthetic division. Show that x minus it is a factor. And now we'll go through synthetic division. Yeah?
So why wouldn't it be like 2x minus x?
So if they tell you something is a root, then x minus it is a factor. Just x minus the number that's a root. That's it. Okay.
On the first step, what is like the C with all lines after it?
Yep, so that's what we're going to do right now. So now you write down the number that, actually I'll just keep it up so you can see it. Write down the number that comes after the minus sign, 3/2. And now you're going to write down all the coefficients of the numerator. 2, -5, 1, 3. I'm not missing any terms, so I don't have to fill in any zeros. And now I'm hoping that when I'm done this problem, I get a remainder of 0. That's my goal. As long as I get a remainder of 0, then I just proved what I circled is a factor. And if that's a factor, that proves that number is a root. Okay. So now, bring down the first term. So just kind of make a line. We need a little more space, but not really a lot of space. So bring down the first term. And now you're going to multiply the number on the outside by the number you just brought down. Well, let's just start with that. Let's multiply the number on the outside by the first coefficient, which is the number we just brought down. What's 3/2 times 2? Yeah, 3. So write the result below the second coefficient. And now it says to add the number you just wrote and what's above it. What's -5 plus 3? -2. All right. And now do it again. Multiply the number on the bottom times 3/2. What's 3/2 times -2? Yep, Catherine. -3. Add the number we just wrote and the coefficient that's above it. What's 1 plus -3? About Nathan?
-2.
Yep, -2. Now do it again. 3/2 times -2 gives me how much? 3/2 times -2?
What do you do? I'm confused on what you did after you did the -5 plus the 3.
So we did -5 plus 3 is -2.
Mm-hmm.
-2 times 3/2 is -3. And 1 plus -3 is -2. And now we're going to do -2 times 3/2 again. Yeah. -3. And what's 3 plus -3? 0. Any guess what that number is that I just wrote down? That's 0? Yeah. That's the remainder. So that means the other part, that's your quotient.
I've done this before. Where have I done this?
Probably algebra 2. So now, I'm just explaining what the last row means. The last row is the coefficients of your quotient. So that's 2x squared minus 2x minus 2. How did I know to start with x squared? Work your way in that bracket. Work your way over. Constant. Oh, no, is it? Constant, linear, squared. So 2x squared minus 2x minus 2. That's my quotient. And my remainder, the last number, is 0. So now what I proved is that if you divide x minus 3/2 into the 2x cubed, I just showed that it divides in without a remainder. That proves it's a factor. Once we know that it's a factor, that means all kinds of things. It means 3/2 is a root. It means 3/2 is a 0. It means 3/2 is an x-intercept. We had a list of 5 things on the board yesterday that all meant the same thing. Okay, well, we're going to do another synthetic division. But any questions on that one? Okay, it's a much faster way to do division, and it takes up a fixed amount of space. Where long division kind of keeps going down and to the right. You just kind of, you need a lot of room. Synthetic division, you don't. Let's do this one. So use synthetic division to find the quotient and remainder. I'm not saying the remainder is going to be 0. Might be anything. If we divide this by that. Now, when we divide, what is it supposed to look like? We're supposed to divide by something that looks like x, and then what? It's supposed to be x minus a number. That's not x minus a number, but it's okay. It's close enough. We can make it x minus a number. What would it be? X minus, yep, minus 3. So that, right there, what I just put a box around, that's what comes after the minus sign, -3. So in this problem, I go back here, that's my C. Okay? It's the number after the minus sign. So that's what you put on the outside. Always put down the number after the minus sign.
So it's just the opposite?
Whatever's right, yep, whatever's right there. Yeah, it's what's after the minus sign. Block that, look at what comes after it.
So,
Now we have to fill in all our coefficients.
so wait, just to figure out the C, it's just the negative or the positive is the number? The opposite?
Yeah, if you see x plus something, it's going to be a minus value for C, and if you see x minus something, then it's the opposite, yeah.
Okay.
Now, what are my coefficients going to be? Yep.
3, 7,
Yep.
0,
Yes.
1, and -11.
Yep. So it's important you put that 0 in for x squared. So now we bring down the 3, multiply, add. Multiply, add. Multiply, add. Multiply, what's that, 61? And then add. What's -11 plus 61? What's that? 17 times 3?
51.
Oh, 51. Thank you. 17 times 3. Why did I do 61? 51.
It would be 4.
And now what's 51 plus -11? 40. And that's it. That's the whole problem, not having to use long division. Let me just double check that we did it right. Actually, I might have just made this one up. Yeah, I just made this one up. So now, let's write out the quotient. So the quotient is going to be that part, constant, linear, quadratic, cubed. So it's 3x cubed minus 2x squared plus 6x minus 17. And my remainder is 40. Now I did go through it kind of quick, so you want to make double check, but I'm pretty sure all the arithmetic looks correct. Except I had 61 instead of 51. But that would have messed up the remainder. Any questions on it? All right, let's try this one. I want to show that 3 is not a root. Okay? I want to show that 3 is not a root. What would that be the same as showing? Yeah?
When you put 3 into like synthetic division to 0.
Yeah, what I'm going to show is that if I divide this by x minus 3, which Angeline just focused on the 3, I'm going to show that x minus 3 is not a factor. By showing it's not a factor, that also means 3 is not a root. Okay? So to show that it's not a factor, I'm going to use the remainder theorem. I'm going to plug in, I'm going to use synthetic division. I'm going to see what the remainder is, and I'm going to hope that it's not 0. As long as I get something that's not 0, it means x minus 3 is not a factor of the numerator, which means 3 is not a 0. All right, so we'll put 3 on the outside. Coefficients, this time I don't need any zeros. And can someone tell me what my first step would be? Yeah.
Bring the 2 down.
Bring the 2 down. Next step. Yeah.
Times 3 and 2.
Multiply 3 and 2 gets 6. And what do I do with the 5 and 6? Yeah. Add them. A little different than long division where you subtract. So a little different. 3 times 11 gives me 33. Plus negative 2 is 31. 3 times 31? 93. Plus negative 3. 90. So I got a remainder of 90. And I'll just write it out. So since the remainder is 90, I just proved x minus 3 is not a factor. Which means, so I just put dot, 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 okay, which means 3 is not a 0, or a root, whatever they call it. 0. Any questions on that? All right, so the strategies for trying to find rational zeros, okay, are we always start with the rational root theorem. Okay, that gives us a list of possibilities. Then use the graphing calculator to eliminate ones that don't even look close. And then if you find one that you think is close, we use synthetic division and we divide through by the root. Because the goal is if you can get your problem down to a quadratic, you can solve it with the quadratic formula from there. But we don't have a cubic formula. So we have to hope that we can find at least one root using this theorem, and then divide through with synthetic division, and then this cubic will turn into a quadratic. So you've got to be able to turn it into a quadratic. And for this problem, that means finding at least one root, because it's a cubic. If it was a 4th degree, you would have to find at least 2. Okay, so if I wanted you to do it by hand, I'd have to have 2 nice places where it crosses the axis. But this one only has to have 1. All right, so let's make a list of our P and Q. So P are all the factors of what number? Okay, 2. Or negative 2, it's really the same thing. But P is all the factors of the constant. P is the factor of the constant. All right, so what are all my factors of 2?
1 and 2.
Just 1 and 2, anything else?
Plus or minus.
Plus or minus. So we don't have many options for P, but we have even less for Q. The leading coefficient is a 1. What are all the factors of 1?
Plus or minus 1.
Just plus or minus 1. So if this is going to have a rational root, what are all the different ways you can write every P over every Q? There's not too many. Yep.
Plus or minus 1, plus or minus 2.
Right. So those are my possibilities. So I'm going to graph it. And hopefully, one of those looks like it works. So we have x cubed minus 3x minus 2. Now, if it looks like two of them work, it doesn't matter which one we use. We just need one. So it looks like, remember I said when something comes up, touches the graph, and bounces away from it, that's usually a double root. So there's probably a double root there. But it looks to me like it definitely crosses at 2. So I'm just going to check it. I could do second calc 0, or I could just type it in, and it is 0. So when x is 2, we get a root. All right, so we've got one. So over here, I'm going to write this like this. If 2 is a root, which I just showed, what does that mean as a factor? Yeah. Well, I need the whole factor.
X minus 2.
Exactly. So if 2 is a root, x minus 2 is a factor. Well, how do you get the other factor? Think about if I said to you, all right, I've got the number 12, and I'm telling you 3 is a factor. How do you get the other one? I mean, we know it's 4, but how would you get it if you didn't know it? Yeah. You divide. Take your problem and divide by what you already know is a factor. So let's take our problem, which is 1x cubed, 0x squared, minus 3x, minus 2, and divide by what we already know is a factor, x minus 2. I'm just not doing the division like we did yesterday. I'm using synthetic division. Now, since we already know x minus 2 is a factor, what am I going to get for a remainder when I do this?
0.
I'm going to get 0. I already know that. I'm not interested in the remainder. I'm interested in what goes there. That's the other factor. That's what I'm trying to get. And once I get that, then I can use the quadratic formula on it if I need to, or factor it. And I think it's going to factor nicely just based on the graph. So we might not even need quadratic formula. So we get 1. 2 times 1 is 2. 0 plus 2 gives me 2. 2 times 2 gives me 4 plus negative 3. 2 times 1 and plus negative 2. We already knew that. There's the other factor. X squared plus 2x plus 1. And that does factor nicely. You don't need quadratic formula to solve it. You can use quadratic formula, but does anyone see how x squared plus 2x plus 1 factors? And it is going to be 2 of the same factor, confirming what we thought, because it goes up and it bounces away from the axis. Yep. X plus 1, x plus 1. I agree. There's your repeated root right there. So now the question is, find all the roots. Oh, we've got 2. That's from the first factor. And what's the root we get from the second and third factor, but it's repeated? Yep. Negative 1. Question on it. Once you get used to it, it's not too bad. It's not the fastest process, but it's not an overly hard process where you have to think about, well, what should I do? You always do the same steps every time. So I got that one. All right, let's do, they're both cubics, so they're really about the same difficulty. Let's find all the rational zeros here. Okay, and then I'll probably skip 8. It's like the same thing. Okay, so let's start with our list. What are the factors of P here? Yeah?
Plus or minus 1.
Yeah, so that's nice. Not too many options there. What are the factors of Q? Yeah?
Plus or minus 6, plus or minus 1, plus or minus 2, plus or minus 3.
Yep. You don't have to write them in order. I just like to. So now, to figure out all your P over Q, there's only one P. So it's 1 over each of those numbers. So if this problem has a rational root, it's going to be at plus or minus 1, plus or minus a half, plus or minus a third, plus or minus a sixth. That's the list of possibilities. Let's graph it and cross out the ones that don't make sense. All right, so we've got 6x cubed minus 5x squared plus 3x minus 1. Let's see if I can make that a little bigger. Okay, looking at that graph, does it look like plus it crosses at plus or minus 1?
No.
I don't really think that's reasonable. Minus a half?
Yes.
No.
Probably not the
Not
minus. How about plus?
Yeah.
It could. I'm not sure yet, but it could be. How about plus a third? It really looks more like a half. Minus a third, definitely out. If you left plus a third, I mean, you could argue that it looks like it could be, but I don't think it is. How about plus or minus 1/6?
No.
No, definitely not. So the only options we have left are plus a half and plus a third. And I really think it's plus a half. So let's try it. Trace. Let's go 0.5. And it is. It's 0.5. Now, you don't have to do synthetic division with 0.5 this time. The reason is because all it said to do was find the rational zeros. So there might be other ones that are irrational, but they're not asking about them here. The rational ones have to be in this list. And the only one that worked is plus a half. You can check plus a third, but it's not going to work. So the rational roots. You don't have to write plus a half, just 1/2. Any question on that one? Okay, so that one, I'm going to skip the upper bound theorem and the lower bound theorem. So we'll finish up with this one. So it's actually the same kind of problem we just did, but now you have to find the rational and irrational. So it's like one step further. Okay, let's do our list of possibilities. You've got to find at least one rational root. You've got to get this cubic down to a quadratic. So we've got to get one. What are my factors of P here? Yeah.
Plus or minus 1, plus or minus 2.
Plus or minus 1, plus or minus 2. How about Q? Yeah.
Plus or minus 1, plus or minus 3.
Plus or minus 1, plus or minus 3. So when I graph this, I'm looking for rational roots. That could be what? Can someone give me, there's 8 of them. Yeah, maybe Angela? Yep, I'll just do plus or minus. So there's 2 of them.
Plus or minus 2.
Okay, so plus or minus 2.
Plus or minus 1/3.
1/3, yep.
And then plus or minus 2/3.
Okay. So now we've got some numbers to look at. Let's graph it and see if any of those seem to make sense. And one of them has to. If none of them do, then we're stuck. 3x cubed minus 8x squared plus x plus 2. Okay, so when we look at it, okay, we're going to get 3 answers to this problem when we're done. Does it look like plus 1 is an answer? I don't think so. It's a little off from that. How about minus 1? No. Plus or minus 2? No. Plus a third? No. How about minus a third? Could be. So I'm just going to get rid of the plus. Could be minus a third. Could it be minus 2/3? No, I don't think the minus is going to work. Could it be plus 2/3?
Yes.
Could be. So the only candidates we have left are minus a third and plus 2/3. So let's check which one works. I go to my table, minus 1/3. No, that's not 1. It looked like 1, but it's not. And then if 2/3 doesn't work, then we're stuck. And it does. So 2/3 is a root. Put that off to the side. Actually, I'll do 2 things. Roots and then factors. 2/3 is a root. That means x minus 2/3 is a factor. Okay? Any questions so far? Now, I'm going to divide through synthetically by 2/3, and that's going to turn this cubic into a quadratic that I can then solve. So we've got 3, negative 8, 1, 2. I already know the remainder is going to be 0. I'm not really interested in that part. I'm interested in the quotient. So 3. 2/3 times 3 gives me 2. What's negative 8 plus 2? Negative 6. 2/3 times negative 6. Well, think of it as what's 2 times negative 6? Negative 12 divided by 3. Negative 4. 1 plus negative 4 is negative 3. And then 2/3 times negative 3 is negative 2. 2 plus negative 2 is 0. So my other factor is 3x squared minus 6x minus 3. What are my other roots? Well, let's look at it. What could I factor out of that? Or what could I divide everything by to make the numbers smaller? Yeah? Divide everything by 3, you don't have to. But now by dividing by 3, I can look at that quickly and I can tell you that's not going to factor. There's no way to factor that. But that's okay, because now it's a quadratic, so how could I get the other 2 factors besides factoring? Yeah. Quadratic formula. So we've got negative b plus or minus the square root of b squared 4ac all over 2a. So I end up with 2 plus or minus, I'm going to be subtracting a negative number, so that's going to turn into a positive. 4 times 1 is 4, plus 4 is 8, divided by 2. And how can you simplify the square root of 8? Yep. After we simplify the square root of 8, yes. 2 square roots of 2. Now you can cancel the 2, because you can cancel it here, here, and here. You have to do it in all 3 spots. So we get 1 plus or minus square root of 2. Those are my other 2 factors. 1 plus the square root of 2, 1 minus the square root of 2. You could easily check it by calculating I'm not going to do both, but I'll just do one of them real quick. Let's calculate this root over here. Second calc 0. While I'm doing this, if somebody can just type in 1 plus the square root of 2 and just tell me what that decimal is. If you do 1 plus the square root of 2, what's the decimal for that? And then plus 1. 2.4142. Let me calculate the root and see what it says. 2.4142. So the answer I got with the quadratic formula is exactly what the calculator gave me. So there's your roots. Okay, so we'll take a look at that more tomorrow in the homework. But I think if you understand synthetic division, that's kind of that's the key for pretty much every problem. All right, so the homework is on 183, and I'm going to have you skip 31 and 32. But I think everything else should be fine. Yep.